So today I'm going to talk on the topic like best of stream plus batch when streaming analytics isn't. So as the title hints, it's a talk about streaming data and some challenges or some use cases around that. And while doing analytics, what kind of problems or solutions we can run into. So a bit of intro about myself. I'm Rohan. I am a committer on the Apache Druid project, and I work as a software engineer at Imply right now. Previously, I used to work on Trino or Presto, popularly known as that engine, and Apache Yarn. So the agenda for the talk will be first discussing a bit of data platform architectures over time, starting from warehouses to streams. Then we'll move on to what can we do with streaming data and how can we handle or consume it. We'll then move ahead defining what real-time analytics is and what can we do with it. And then we'll enter the Druid and we'll see how can it solve some of the problems that come while doing real-time analytics. Right, so starting with data warehouses, so since 70s, this has been a very popular architecture which people have used for doing data analytics. Like generally, the data was coming from operational databases and it used to get ETL'd into a data warehouse. And the data warehouse was supposed to be like a specialized system with good hardware running, and it used to have like a closed format, and the engine used to be super optimized for querying. And the things that people used to do was to do like maybe do some batch analytics, some reporting, and also at that time like data mining, etc. was very popular, which was being done on data warehouse. So the good thing was that it was a tightly coupled architecture with storage and compute, but the problem was that it had a limited flexibility, but it ran very fast and it supported like some specialized use cases. Yeah, so from the last decade or so, there has been introduction of a data lake architecture, which built upon some of the problems which were observed in the data warehouses with time. So there were two aspects to the problems. One was regarding the cost. So since everything was tightly coupled with less flexibility, you mostly had to pay for the peak usage to a data warehouse. And the second problem that was there was that as apps and the data was getting more diverse, you would need to get data out of the data warehouse and put it in somewhere else to do more analytics. For example, things like ML or running some time series databases was getting pretty hard on data warehouses. So what people decided was to throw away the closed formats. They decided to introduce open formats like Parquet or ORC and write all their data from the data sources into a data lake, which is built upon some cheaper storages than what was being used for data warehouses. For example, like HDFS and cloud storages then became very popular as a source for data lake. And then you used to run a ETL using MapReduce and Spark and then re-ingest it in the data lake. So what the goodness of the cheaper storage brings in is that you can just push any kind of data into the storage and then just recompute it and then also land it again back to the data lake. So now what we get with the data lake architecture is that we get a wide diversity of use cases or apps that can use the data. So the first one is the SQL, which was more popular with data warehouses. So there have been multiple query engines like Trino, Hive, or Spark, which directly allow you to run SQL over data lake. And then there were softwares which were running ML AI, like PyTorch and other things, which also run on raw Parquet files and can just directly ingest them and make them queryable for your models. And then there was another set of apps which are specialized databases like time series databases or graph databases. They can also directly ingest from the data lake or directly query the data lake as well. So you get a wide variety of things with cheaper storages as well, right? And I think recently there has been an introduction of a concept called Lakehouse, which tries to build upon the goodness of data lake and the performance of data warehouses as well and combine them both to bring something to the users. While we think all this is good, we think that in the future, the de facto standard will go towards streaming, because streaming architectures are more true to life and they enable like better decision cycles because the data is very real time. So what we see in this architecture is that your data directly goes to an abstraction called a stream hub. A stream hub can be something like an Apache Kafka or Amazon Kinesis or something like that. And you're ingesting into the stream hub as soon as your data is generated. And then you're running your ETL or any kind of transformation that you want via stream processors. There are multiple stream processors that are available like Flink, Spark Streaming, etc. And then you ingest it back to your stream hub. And what happens in this architecture is that you get a level of indirection Whereas you can see the last thing that you can do is that from the Stream Hub, you can again use the data lake architecture. You can archive the data in batches and put them into a data lake, which can again then get used by multiple apps. But the two new things that you get is that there can be databases which can directly work on streaming data, and that can ingest them, and that can make them queryable. And the third thing that you can get is a streaming analytics system where, let's say you are running on a Stream Hub, there are some things that you can do directly on the stream, as was also presented in the earlier talk, that people are trying to get some data directly on the stream as well. So thinking a bit more about the streaming platform, this was a nice picture put up by Confluent, the company which steers Apache Kafka. They have been advertising this picture, and they say that this is an easy way to build a streaming platform. And there are nice arrows. This picture is neat, and it points to different things, and there is a data warehouse, Hadoop, and all those applications, etc. as well. But if you think about it a bit more concretely, there are multiple questions in it, which requires a bit more thinking. For example, like there is this thing called monitoring. What kind of monitoring does it imply? Is it just alerting, observability, or is it some performance metrics observability that you want to do? Then there is some security. There is no idea what kind of security does that imply. Is that an application or some requirements, or is it just put to make some people happy so that there is some sort of security in the system? And then there is search and NoSQL on that side as well. And what kind of things are those? Are they applications, or do they need applications to query, and that kind of things? So it becomes a bit complex if we start thinking of a streaming platform just from the get-go. So talking about something simpler, I would like to just take this simple slide and see what we can do with streaming data. So this is a very simple slide. It says that you have an application and you have a streaming hub library, and you just put the data into a stream hub. That is a simple thing that you can do, and you have ingested your data now to the stream hub. Right. Another popular thing that happens is that a lot of times the apps, they maintain their state in a transactional database, like generally how we write our applications. And then those transactional databases provides a change stream, and that change stream is then ingested into a stream hub. There are softwares which convert those change stream into events, which can be then put into stream hubs. But that is also a very common way of putting things in a stream hub. Like once we have put data into stream hub, there are ways through which we can get data out of it and what we want to do with it. Right? So one way is to use Kafka Connect and Kinesis Firehose. They provide multiple connectors for your enterprise data warehouse and data lakes, and you can just pull data out of your stream hub and then just put it in a database, which we commonly know as a streaming data pipeline. Right? Another common usage of stream hubs is communication between services. So in the microservices architecture, a lot of services contact each other via stream hub. So stream hub acts like a pub sub for different services. One service ingests something, and the other services subscribes on it and reads something. And the goodness that comes is that you get decoupling of services, and the reliability of services increases because a failure of service one won't necessarily take down the whole service too. While this is not related a lot to streaming, but this is a popular thing that people do. So now coming back to streaming data and the analytics on top of that, if you just try to search what are the top streaming analytic products, things like Apache Flink, Spark Streaming, IBM Streams, Azure Stream Analytics, and those things come up. There are more things, like all the clouds provide their own solution, and then there is Kafka Streams, KSQL, Flink, Spark Streaming. But the question is that given all those things, what do I need to do? What can I do with those things and my stream hub? So the simplest thing that you can do is, from a stream hub, you can use a stream processor to generate some alerting and API calls. For example, in the last talk, it was explained that the Raspberry Pi was generating some kind of an alert under some situation where it turns a red light or something. A common alerting thing can be detecting attacks, frauds, or just knowing that something wrong is going or something absurd is going on in the system. Or you can do API calls where, let's say, you can get the data from stream hub into a stream processor and then do capacity planning, etc., just doing some API calls in your system. The next most common thing that you can do using a stream processor is to push the data from the stream hub and then put it into some storage. Something like HDFS or cloud storage is also a very popular way of pushing the data from the stream. Using the stream processors, you do something and then you push it into a storage. Now what you can do with stream processors as well is that you can write a continuous query. With a continuous query, you can join multiple streams at runtime, or if you have a static set of questions which are important to you, then you can stream the data through those questions and generate some new data, which you can again re-ingest back into the stream hub. And then the stream processors, they just put it into a storage system. So now that we have some semblance of something going on and creating some queries or some processing of data in the stream hub, now let's say we want to build a real-time dashboard. Now what we would need to do is that we are doing some processing via the stream processors that is generating some state. Now we would want to generally put them into a key value store, since they are generally very fast for clients and they provide some kind of querying capabilities over the data which is stored on them. So that is what a lot of people do, that they process their data via stream processors and they have a static set of queries, etc. And then they push it into some KV stores. And then that KV store can plug in your real-time dashboard. So now you have something which refreshes periodically and produces results which you can see and feel good about. There are some stream processors, I think at least Flink does it, which provides you access to even the state which the processor is maintaining. And you can directly use that state to create the real-time dashboard. And that state access or this stream processing either can be done via like a streaming job or like SQL, which is getting more popular with the stream processors these days. So like this is something that you can get via stream processor, and you can get to a real-time dashboard via that. So as mentioned, like the stream processors are doing continuous query, and there is an unemitted state which is maintained by the stream processor that you can directly access. And then there are KV stores where you are actually pushing your processed data or your processed queries, over which you can do simple things like key lookups or short scans or some pre-computations. So this is what kind of a real-time dashboard would look like with stream processors. But the question that we want to ask is that, like, that thing is good, but is that enough? So the problem that I want to point is that, can we do something like this with stream processors? So what we see here is that a lot of clicks are going on, people are selecting some things, people are grouping on some things, there are lines, charts, graphs, etc. Generally, I believe that it is a bit difficult to do that using the stream processors, because this kind of interactivity requires some other things which the stream processors don't provide. So more formally putting, if you want to do a slice and dice of big data streams, then you are running into a newer set of problems. Then maybe you need data for a longer time, which means that your stream processor now has to think about things like storage systems and the layouts in which the data is stored, which makes it a bit complex for them to do. Also in the GIF, you saw that there was an interactive exploration. What it means is that someone is continuously trying to interact with the data and continuously trying to fire queries, which makes it hard in terms of concurrency for the stream processors to handle. And what happens a lot of time is that you see some absurdity in your system, and you want to then look under the hood of all the reports and the dashboards. And you want to find out maybe some root cause of some good or bad thing that is happening. So that requires some drilling down and some advanced analytics that you want to run, which is a bit hard to do on stream processors. And we also want to maintain that our data is fresh too, so that we don't lose the essence of our real-time data. So a system that is trying to solve all these problems has the following challenges laid out for it. So the first one is scale, because when data is large, you need a lot of servers, you need a distributed service which can scale easily to handle the load. The speed that this engine should aim for should be a sub-second response time, because mostly these things are powering some UI, either internal or external users are trying to use it. And generally, I don't think anyone likes the spinning wheel on a UI. So sub-second response is not like a good to have thing in the system. It should be a good expectation, or like a thing that it should easily support. And then there should be some ability to do complex analytics, since like you can't pre-compute everything, so the system should be responsive in an ad hoc manner. And generally the event data is highly dimensional, so it should be able to handle hundreds of dimensions. And as we discussed, the interactability kind of introduces more concurrency, as many users would want to use that, and there are many tenants. And again, we still don't want to lose the freshness from these streams that we get. So here we introduced like Druid, which is a high performance analytics data source for event-driven data, which tries to tackle all those challenges. Since these are a lot of keywords, we'll try to go over them in a broken manner. By high performance, we mean that the query latency is low. We promise that, okay, sub-second is a real thing and a consistent thing in our database. And you can also ingest at high rates as well. So if there is a lot of data coming from your applications, you can have a central database where you can push all of them. By analytics, we want to tell that we do support complex things like ranking, group by, time trending, counting, all those things like complex aggregations. You can do all that. The data stored part means that the cluster actually stores a copy of your data. So while it is ingesting from the Stream Hub, it has to maintain a copy. The goodness that comes out of that is you get a high performance query engine. And it is based for event-driven data. So where the most common examples for event-driven data are like click streams, network flows, where let's say you have a network mesh and you want to measure how my network system is doing. And let's say if you want to measure user behavior for your application or some digital advertising that you want to do. Or if you, let's say, if you have a server fleet and you have the data which is coming on from all the servers, which are the server metrics, which is more like a time series data that you want to analyze. And then there is IoT data as well, which is similar to time series, but yeah, I mean, that is also handled. So we looked at a while back at this image, and this showed that there was this thing like stream processor, etc., all those things, and KV store for building a real-time dashboard. So Druid claims to replace that with just an analytical database, which gets a continuous load of things and does its aggregation and serving layer both inside the system so that you don't have to take care of. And then there is a SQL API through which you can query. The earlier GIF that we saw was from an Imply proprietary software, which is like a dashboarding software like your Tableau and Looker and Superset. But you can plug in Druid to any of your favorite apps which you want to use for dashboarding. So like getting our feet wet into the key features of the software. So here are some of the things which represents the scalability, reliability, and the general capabilities of the system. So the database is actually column oriented, and that's how it can handle a lot of dimensions, since generally the analytical data kind of runs out of hand in terms of breadth, and a lot of dimensions keep adding and gets put down as well. So the column oriented storage helps in the compression as well as querying part of the system. The high concurrency part comes also because you can very elastically scale the database to support a lot of users. And by high concurrency, I mean that a Druid cluster can easily scale up to thousands of users running maybe even 10,000 of queries per second as well. So as we discussed that we wanted the system to have some big data streams to analyze. So it should be scalable. It's a distributed service and it can scale to hundreds of servers, and the ingestion rate can be as high as 1 million events per second as well. Now the good thing that comes with all this is that you can do all this along with maintaining isolation and cost efficiency. So for example, let's say in a Druid cluster, there are multiple subsystems. Let's say one subsystem is trying to ingest something and the other subsystem is trying to querying. It is not necessary that both of them have the same hardware or the same capacity. You can just plug out the system that you want, scale it how you want it, and they all will be a part of the same system. And since Druid powers a lot of UI and customer-facing applications, we have built in a built-in high availability of the coordinator, which helps in reliance of the system. And then there are enterprise security features, which includes transport layer security from client to server and within the cluster as well. And then there is authentication and authorization with all the popular tools like LDAP, Kerberos, and native authorization as well to different resources. So talking a bit about the features of the ingestion subsystem, which is a very major subsystem of Druid. You can, as promised, you can do continuous real-time ingest, and it can also handle late arriving data, which is very common with real-time data, that sometimes the clients hold back the data and then you kind of push it again back. Right? And you can also actually do batch ingestion. Let's say if you have some data in your data lake, you can use any of the popular formats like ORC, Parquet, JSON, Avro, all that. And you can ingest it via using a SQL or a JSON spec. The good thing with batch ingestion is that you can also do range or hash partitioning if you want fast querying. The partitioning of data is a very useful thing. It helps 10 or 20% of the query performance as well. Another good thing that you get out of ingestion is that you can do automatic compaction of data that you have ingested. So for example, what happens a lot of times is that when the late arriving data comes, it is pushed into small files, and that creates a lot of problem while querying because the number of files, etc., they increase. So you can compact them and create like a nicely structured data. Or if you want to kind of reduce the resolution of your data, maybe you want to aggregate some things. Earlier, let's say for the current day, you are evaluating your data at a per second level, but for the previous day, you want to do that per minute. So you can do that all via a compaction job. And another good thing that comes is that you can also do aggregations at ingestion time as well. So as you are ingesting, if the data is too much, you can ingest it at runtime, compact it, and then store it. And there are also like expression transforms that you can use. The query system, it provides like the SQL API. You can do that both via REST and JDBC. The JDBC one is very important for all the tools that connect, right? And by default, you get bitmap indexes and dictionary on all the dimensions, which make things very kind of performant in the sense that you don't have to materialize the data while querying it. And like a lot of times, you can do database features like late materialization and working on indexes and dictionaries to do fast computation. Then there is schema elasticity and evolution as well. So there is no relational tying of your database where you specify like a schema and you have to stick with it. And if you want to change it, then you have to rewrite all the things. So Druid doesn't provide for all those problems. You can just change the schema on runtime and the queries will just evaluate them automatically. Although join is a kind of an anti-pattern in the OLAP world, but still we provide it because we have seen enough exceptions in the production systems that we provide join. There is support for JSON columns, which are the most popular thing through which event data gets generated, and there is automatic indexing of things so that you don't have to care about how to index it for performance. And then there is actually a very extensive support for approximate algorithms as well, because generally while processing real-time data, people do want to get approximate results instead of spending time and evaluating the exact results. So there is a very good friendship with Apache Data Sketches project, which provides like specialized approximation algorithms for quantiles, double, and strings, etc. And if all this jazz is not enough, then you can also add your own aggregation functions, filters, scalar functions, etc., and easily plug in the system. So as we discussed, the use cases are mostly related to clickstream, checking your app behavior, user behavior, digital advertising, performance, network flows, and IoT. So a lot of companies have been using Druid. I think it's 10 years young now. And like people like Yahoo, Netflix, Airbnb were very popularly and are at a very high scale using the software. There are multiple telecom companies which also use it as well. And the original creator of the Druid project was Meta Markets, which was running like a derivative market over the ad tech system. So there was some testimony from Yahoo which was saying that they have billions of events which are being ingested into Druid, and all of them were getting scanned within a second. So given that all those things, if we look a bit at the architecture of the system, we can see that there is a client and there is a query node which acts like a broker between the storage system and the client. So the query node takes in your query, provides you a console to write stuff that you want to query, and then it interacts to the main cluster, which is in the blue section. And as you see, all the nodes in the cluster are doing the two subsystem parts. One is indexer, which is indexing data either from streams or from batches, and one is the historical data, which maintains your batch data, which you are ingesting over the time and is served over querying, right? So every node can do both of that. And the good thing is that both the systems are not directly coupled. They interact via a bridge called deep storage, which you can set up something like an HDFS or a cloud storage. So you have the elasticity to push the data from indexers into a deep storage, and then the historical will then download data from there to serve. And then there is a master node which performs all the coordination duties, and it does the election and the high availability using Apache Zookeeper, and there is a metadata store where you put in data regarding the table or the streams that you have stored. So we discussed a bunch of things that Druid provides, and like these are some of the main reasons why these things work. Like for example, like a sub-second query is possible via indexes because they save a lot of work, and you can work directly, especially if there are strings, etc. You can directly work on dictionaries instead of kind of deserializing them and then using them. Then there is our processing engine is fully vectorized, which means that we are not spending all that problem or the time that you have in the per row processing thing. We do things in batches. Since Druid is a Java-based project, there are chances that you run into a JVM problem while doing memory management. So we have done like an efficient and a fast direct memory-based execution where you don't have to run into the overheads of Java memory and also the slowness that might come due to GCs, etc. Along with that, for aggregations ranking for all the querying system, we extensively use the dictionaries for performance implementations, so that if you can do something directly on dictionary, why read the data and spend time on it? And if push comes to shove, and if we have to scan tables, that is also being done very efficiently in the Druid project. We currently use like the mmap system call of the operating system. So if your workload has some hot columns or has some data pattern, that automatically gets adapted into the mmap, and your table scan eventually starts becoming more memory driven instead of disk driven. So if we look at a bit of integration patterns that come via for Druid, we can see that the event streams are pushed into stream hubs, and you can enrich them by the stream processors and then directly push them into Druid. This is the modern architecture or the modern way how people do things. Then there is slightly less modern architecture where via data lake, you enrich data using Spark or Hive and then ingest into Druid. Those people do generally batch ingestion. So we recommend you to try this at home. You can download it from the Apache community website, or the Imply distribution is also available. And if you like contributing to open source projects and if you like coding things, then feel free to come here at github.com, and you can pick any issue or open issues or work on any PRs, etc. And also we have the community which is going on Twitter and on the community page of the website as well. Recently we have launched a Slack community which is getting very popular, and people come there to discuss their problems, thoughts, and solutions. So that is something also that you can check out. Thank you. I think that's it from me. Thanks.